What if one of the brightest and closest dying giants in our sky was hiding changes so massive, so turbulent, that they're reshaping its entire fate right now? What if Betelgeuse, the red shoulder of Orion, the star that has watched humanity for thousands of years, was in the middle of transformations far stranger and more violent than anyone imagined? What if the dimming you saw in 2019 wasn't a coincidence, but a clue that something deep inside its core is shifting? Welcome back, traveler. Tonight we drift through science. You're lying wherever you've chosen to rest, maybe in your bed with the lights low, or with headphones soft against your ears, listening while the night settles around you. If calm astronomy like this helps you unwind, you're always welcome to leave a like and subscribe so this quiet corner finds more people who need a gentle way to learn. For now, just let the room soften and let Betelgeuse glow faintly in your imagination. You might be awake because your mind won't settle, or because tomorrow feels heavy, or simply because sleep takes longer some nights. It's okay. You don't need to follow every scientific detail or remember every number. You can drift in and out while we explore what's happening inside a star 550 light-years away. Your focus can wander. You're not here for a test. You're here to rest while something vast and ancient unfolds above you. Tonight we're going to walk slowly through the real physics of Betelgeuse's interior, its collapsing core, its turbulent convective cells, its helium-burning shells, the massive plumes rising larger than our entire orbit, the shock waves passing through its outer layers, and the gas it's shedding into space like a slow, unsteady exhale. We'll see how telescopes like the VLT, ALMA, Hubble, and Gaia piece together clues. Dusty plumes, surface hotspots, wandering brightness curves, irregular pulsations, spectral fingerprints. It's the universe out there, but also the humans down here adjusting mirrors, cleaning detectors arguing over data pipelines, and chasing patterns in the noise. So tonight we'll walk gently through the strange, morinous, unstable heart of a dying red supergiant. You don't need to try hard. You can relax your shoulders, let your breath fall into a slower rhythm. Dim the screen if you want, and allow your thoughts to float the way starlight drifts across the void. Somewhere far away, Betelgeuse is swelling, contracting, shaking itself apart one layer at a time. And now, as you settle deeper into the quiet, our journey into its glowing interior begins. You picture yourself drifting above Orion's shoulder, looking down at Betelgeuse the way a quiet observer might watch a bonfire from a nearby hill. From this imagined vantage, the star doesn't look steady at all. It swells, shrinks, trembles. You can almost feel those slow pulses pushing against the darkness, like the breath of something enormous struggling to stay balanced. Even from so far away, there's a sense of tension, as if the whole star is trying to find a rhythm that keeps slipping out of reach. Inside Betelgeuse, the source of that trembling is raw physics. The core is burning helium into carbon, creating shells of fusion stacked like layers of a trembling onion. Those layers don't sit still, they heat up, expand, cool down, and then collapse again. Each cycle releases or removes pressure. When the pressure inside rises too quickly, the star expands. When it drops, gravity pulls everything inward. These oscillations are called pulsations, and they're one of the key reasons Betelgeuse flickers unpredictably. The size of these pulsations is staggering. Some of the convective cells, massive bubbles of rising plasma, are the size of Earth's orbit around the Sun. Imagine a single bubble floating upward, carrying heat from deep inside the star, stretching a glowing surface outward by hundreds of millions of kilometers. These cells rise slowly, then cool, then sink back down in a kind of stellar roll that repeats over months or even years. Every bubble changes the star's brightness, shifting it by amounts visible even from Earth. You can imagine standing, weightless, just above one of those giant rising plumes. It would look like a glowing continent slowly emerging beneath you, brighter in some patches, darker in others, all of it boiling quietly like a massive sea of red-gold magma. The heat wouldn't feel like warmth, it would be overwhelming. A rising shimmer that ripples the space around you. From up close, the surface wouldn't look smooth, it would look alive. Astronomers first realized how chaotic Betelgeuse's surface is by using interferometry, linking the very large telescope's multiple mirrors to act like a single enormous eye. In 2009, these observations produced something astonishing. Betelgeuse doesn't have a uniform disk. Instead, there are hot spots, cold spots, dim patches, and bright arcs. In 2019, during the Great Dimming, the VLT imaged a portion of the star that had visibly darkened, shocking astronomers around the world. This technique works by combining the light from telescopes spread out over vast distances, allowing scientists to see detail in stars that would otherwise appear as simple glowing dots. The raw data looks like scrambled noise, tiny peaks and dips in brightness. But after weeks of calibration and code tuning, an image emerges. You imagine scientists leaning over screens, adjusting algorithms late into the night, arguing over artifacts, wondering if the star is changing or if the error lies in their instruments. When you think of Betelgeuse's surface, it helps to picture a pot of thick soup simmering over a low flame. The top layer bulges and collapses, shifting unpredictably. Hot spots appear where bubbles rise, fade, and sink again. That's essentially what's happening, but on a scale that defies comprehension. Where a bubble in soup is centimeters wide, a bubble in Betelgeuse is hundreds of millions of kilometers across. This constant rising and sinking affects the star's brightness in ways that seem almost personal. Some nights, the star looks bold and steady. Other nights, dimmer, subdued, as if tired. To ancient observers, this made Betelgeuse feel alive. To modern observers, it reveals how violently unstable a red supergiant truly is near the end of its life. You're hearing the slow heartbeat of a star that's running out of ways to stabilize itself. The instability stems from the fact that Betelgeuse is burning fuel in multiple shells at once. Deep inside, helium is fusing into carbon. Above that, thinner shells fuse hydrogen into helium. And above those layers, convection drags heat outward in massive currents. Each layer expands and contracts independently, creating internal pressure waves that slam into one another like deep cosmic echoes. You can imagine those pressure waves the way you might imagine sound waves moving through a cathedral, bouncing, intersecting, amplifying each other. But inside Betelgeuse, the walls are made of plasma, and the echoes are shocks of pressure and heat that can distort the star's exterior by millions of kilometers. The star isn't just beating, it's shaking itself apart one slow oscillation at a time. One of the strongest pieces of evidence for these internal shifts comes from photometry, the precise tracking of brightness over long periods. Observatories like AVSO, Gaia, and countless small telescopes record Betelgeuse's light curve every night, creating a kind of diary of its mood swings. These curves reveal multiple overlapping cycles, a short one around 400 days, another longer one around 2,000 days, and irregular fluctuations layered on top. Picture a wall covered in line graphs, each one representing a different year of Betelgeuse's life. Some curves dip suddenly, others rise, others jitter with no clear pattern. Astronomers trace the lines with their fingers, trying to spot hidden rhythms. The dimming of 2019 stands out as a dramatic plunge, a drop so fast and deep that for a moment, everyone wondered if the star was about to explode into a supernova. The Great Dimming was ultimately traced to a combination of events. A massive convective plume burst from the star's surface, cooling rapidly, creating dust that temporarily obscured light. Hubble caught the early signs, ultraviolet emissions from hot material pushing outward, before anyone on Earth suspected what was happening. It's rare for us to catch a star in the act like this. Imagine that moment in 2019 as a kind of cosmic cough. Betelgeuse expelled a huge bubble of gas, which then cooled into a cloud of dust. That cloud drifted into our line of sight, dimming the star by nearly 40%. It wasn't dying. It just had an eruption, a shedding of outer layers. Stars this old don't behave neatly. They stagger, flare, sputter, and pulse. You can think of this behavior the way you might think of an old lighthouse on a stormy coast. Sometimes the light shines clearly through the fog, other times the wind whips moisture across the lens, dimming the beam. The lighthouse still stands, still turns, but the environment around it makes its signal unpredictable. Inside the star, the core continues to shrink, heating slowly, while the outer layers wobble with each new pulse. These pulses are like deep breaths taken by something that has climbed a long mountain and now struggles to catch air at the summit. Each contraction forces heat outward. Each expansion allows gravity another chance to pull everything inward. This breathing isn't gentle. Models show that the interior density changes by large factors during these cycles. One moment, the star is pushing outward with incredible force. The next, gravity takes the upper hand. It's an internal tug of war that will continue until the core collapses for good. When astronomers run computer simulations of Betelgeuse's evolution, they do it in rooms lit by the glow of multiple screens. Lines of code scroll. Simulations render slowly. Some runs crash. Others take hours or days to complete. The scientists drink cold coffee, adjust parameters, rerun the models, and sometimes stare in silence when the results don't match their expectations. Those simulations suggest Betelgeuse is burning through the last of its usable fuel. Not today, not tomorrow, but in cosmic terms, soon. The core temperature rises relentlessly, nudging the star closer to the moment when it will no longer resist gravity. But for now, the star keeps pulsing, shedding, swelling, struggling. You lying in your quiet room listening to all of this are connected to a star in its final chapters. While you breathe slowly in the dark, Betelgeuse takes massive, slow breaths of its own, each one measured in months or years. Its heartbeat is irregular, but it's still beating. And even though we're far away from it, the light that reaches you tonight left the star around the year 1470. When you imagine Betelgeuse pulsing, you're really imagining something that happened centuries ago. The star you see is a memory. That thought brings a kind of peaceful perspective. You don't have to grasp every detail to appreciate the enormity of what's unfolding out there. You're simply listening while a dying supergiant struggles through the final chapters of its life. And as the star oscillates in the darkness, another layer of its strange internal story unfolds, waiting for you to drift deeper. When you imagine drifting closer to Betelgeuse, you begin to sense something beneath its trembling outer layers, a deeper tension, like a quiet pressure building under a mountain of glowing gas. You picture yourself sinking through the swollen atmosphere, slipping past the vast convective cells, moving down through layers of shimmering red-orange plasma. As you descend, everything grows denser, hotter, and more unstable, as if the star's entire interior is rearranging itself in slow, uneven waves. Deep inside, the core of Betelgeuse is shrinking. It's only a fraction of the star's size, but it contains most of its mass, squeezed down by gravity into a dense, burning sphere. This core is no longer fusing hydrogen, it's burning helium into carbon and oxygen in a shell-like structure. Around that, thinner shells fuse hydrogen. These shells don't burn steadily, they flicker and flare, creating pulses of heat that travel outward. At the temperatures inside Betelgeuse, often exceeding 100 million degrees Celsius, matter behaves differently than anything familiar. Electrons are stripped away. Atoms are reduced to bare nuclei. The interior isn't gas or flame. It's plasma so dense that light takes a long time to escape. Any photon created in the core might bounce around for thousands of years before reaching the surface. You're not looking at light from the core, you're looking at echoes. Scientists estimate Betelgeuse's radius at roughly 700 to 900 times that of the Sun, depending on the pulsation cycle. If you placed it where our Sun is, its outer layers would reach somewhere between Jupiter and Saturn. Models from the Geneva Observatory suggest the core is comparable in size to the Earth-Moon distance, yet contains more mass than the entire Sun. That contrast, tiny size minus massive density, is the engine of everything happening now. You might imagine hovering near that core, sensing the immense crush of gravity around you. Space feels thick, as if even the emptiness is pressurized. The closer you drift, the harder it is to picture anything stable. The forces here aren't gentle, they're relentless, ancient, and indifferent. You feel like you're floating inside a furnace wrapped in layers of trembling molten air. Telescopes can't see inside Betelgeuse directly. Instead, scientists rely on modeling software that simulates red supergiant interiors using physics, nuclear reaction rates, opacity tables, convection equations. These models run on supercomputers, calculating thousands of time steps, each one representing years or even centuries of stellar evolution. The output includes temperature profiles, density maps, pulsation frequencies, and predicted brightness curves. Sometimes, the results don't match real observations, forcing researchers back to the code. Those researchers often work late into the night, adjusting turbulence parameters, comparing model brightness curves with Gaia's photometry, calibrating against interferometry from the VLT. They talk quietly across glowing monitors, debating whether a strange oscillation in the data comes from the star or from an error in the atmospheric correction software. Betelgeuse has become a kind of cosmic puzzle they pass around between them. Inside the star, convection dominates. Hot plasma rises from deep within, cools as it expands and sinks back down. But convection in Betelgeuse doesn't behave like convection in the Sun. In the Sun, there are millions of convective cells. In Betelgeuse, there are only a few dozen. Each one is enormous, vast columns of rising material stretching across the star's surface. A single cell can last years, reshaping the outer layers with each ascent. Imagine yourself drifting alongside one of those massive columns. You see it rising slowly beneath you, glowing brighter than the surrounding haze. The plasma churns, folding and curling in shapes that look almost like slow-motion waves. From a distance, it resembles a red ocean current. Up close, it feels more like a living thing, a great hot creature pushing upward in silence. The internal temperatures are so high that even the speed of sound changes. Deep in the star, sound waves travel at hundreds of kilometers per second. These waves create pressure ripples that move outward, shaking the outer layers. Some of those ripples reach the surface, contributing to the visible pulsations we measure on Earth. When you stare at Betelgeuse in the night sky, you're seeing the distant shimmer of these internal quakes. One key piece of evidence for these internal pressure waves comes from spectroscopy. Splitting Betelgeuse's light into colors and analyzing each wavelength. Lines in the spectrum shift slightly depending on whether parts of the star's surface are moving toward or away from us. These shifts reveal motions of tens of kilometers per second, far faster than any earthly wind or weather. It's a storm on a scale the human mind struggles to grasp. Spectroscopists often spend long nights aligning equipment, checking calibration lamps, cleaning dust from detectors. They take exposures in intervals, adjusting for atmospheric turbulence, clouds, or even vibrations from passing cars near the observatory. When they finally see the Doppler shifts in Betelgeuse's spectrum, they're reading the star's heartbeat in real time. Metaphorically, you could think of the core as the beating heart and the convective layers as the lungs. The core contracts, heating up, then sends energy outward. The outer layers swell, cool, and contract. It's not a perfect analogy, but it captures the rhythm. A massive, lumbering breath, thousands of times slower than your own, but far more powerful. Reflecting on this giant, trembling interior brings a strange calm. Your worries, tomorrow's tasks, unfinished conversations, unanswered messages, feel small compared to a star wrestling with gravity and heat in its final era. Betelgeuse has existed for millions of years, burning through stages of life in bursts of fusion and collapse. You're just listening, breathing quietly, while a massive star struggles through its final transformations. Another important layer inside Betelgeuse is its helium-burning shell. When helium burns, it produces carbon and oxygen. The core is gradually filling with these heavier elements. As the core contracts, it heats further, inching toward the next stage of evolution, carbon burning. But Betelgeuse isn't there yet. Carbon burning requires even higher temperatures, and Betelgeuse is still slowly preparing for that leap. The energy released from helium burning causes the outer layers to expand enormously. These expansions increase the star's radius, making it puffier and less dense overall. That's why red supergiants have such low surface gravity, so low that material can be lifted from the surface and blown away by stellar winds. Betelgeuse is constantly shedding mass, losing about 1 solar mass every 100,000 years. Imagine drifting near the boundary where gravity weakens. The sense of weight fades, plasma and dust lift into the air like fine smoke. The star's outer layers feel delicate, almost fragile, like the loose rind of a fruit that's become overripe. The boundary between star and space becomes blurry. Astronomers use instruments like ALMA, the Atacama Large Millimeter Submillimeter Array, to measure this escaping material. ALMA detects the cold dust around Betelgeuse, mapping its outflows. In images, the material appears as arcs and clumps drifting away in slow motion. Each clump is evidence of a past pulse or eruption, frozen in space as the star continues its unstable cycle. Seeing these dusty arcs feels like looking at the rings inside a tree trunk, each one representing a moment in history. For Betelgeuse, the dust records years of eruptions, shedding, and contraction. It's a chronology of turbulence written in slow-moving clouds. You lying here in the quiet, listening to this story, share something unexpected with Betelgeuse. Neither of you knows exactly what comes next. The star may take centuries to reach its final collapse, or it may transition sooner. The uncertainty is real, but the timeline is vast. You're simply observing a chapter, one moment in a long, dramatic cycle of stellar evolution. Thinking about the core contracting and the outer layers trembling gives you a sense of perspective. Your own life feels faster, more transient, more delicate. But in another way, there's comfort in knowing that instability is universal. Even stars wobble. Even giants falter. And as Betelgeuse continues this deep, slow transformation, you drift alongside it, curious, calm, listening to the subtle vibrations of a star caught between its past and its inevitable future. As you drift in your imagination between the shrinking core and the trembling surface, you begin to notice the vast middle region, an enormous zone where energy struggles upward in great heaving currents. It's a place of constant motion, like the inside of a thunderstorm that never ends. These are the convective layers, and they are responsible for much of Betelgeuse's strange behavior. You picture yourself floating inside those rising columns, feeling the slow, powerful push beneath your feet. In these layers, energy moves primarily through convection, hot plasma rising, cooler plasma sinking. Radiative transfer, which dominates in many stars, becomes inefficient here. The opacity is too high, and photons scatter endlessly. So Betelgeuse relies on physical movement of material to transport heat outward. It's a process both simple and chaotic, like watching boiling water but on astronomical scales. The temperatures in these intermediate layers vary dramatically. Near the bottom, close to the helium-burning shell, temperatures can exceed tens of millions of degrees. Higher up, they drop to a few thousand degrees. This huge gradient drives the convection. Hotter pockets move upward, carrying energy with them. Cooler pockets fall inward, completing massive circulating loops that churn the star's interior. To understand the scale, scientists estimate Betelgeuse's convective cells to be so large that each one contains more mass than several Earths combined. The movement is slow, often just a few kilometers per second, but over millions of kilometers, it becomes profound. It reshapes the star's outer layers and influences its pulsation cycles. You might imagine drifting into one of these rising plumes. The plasma below you glows with a dull reddish hue, swirling like thick smoke under a strong updraft. You can't feel heat in this imaginary space, but you sense motion everywhere. The entire region seems to ripple, as though the star is breathing from the inside out. One of the strongest clues about this convection comes from the star's granulation patterns. Interferometric images from the VLT and Cara array have revealed bright patches and dim regions across Betelgeuse's surface. These aren't spots like those on the Sun, they're much larger and more dynamic. Each patch corresponds to a region of rising or sinking plasma far below the surface. Scientists studying these patches often work with raw interferometric data that looks like splotches and interference fringes. They use image reconstruction algorithms, Mirror, Squeeze and others, to turn that noisy data into coherent images. The results sometimes surprise them: asymmetric surfaces, large bright arcs, structures that clearly shift over months. Betelgeuse refuses to look like a simple star. Thinking about these patterns is like watching a fire from close up. The flames leap and twist, sometimes bright, sometimes dim, each movement revealing a different shape. Betelgeuse behaves similarly, but the flames are enormous convective plumes. In the middle layers, there's also a strange phenomenon called overshoot. When rising material reaches a stable region, it doesn't stop immediately. It pushes upward past the boundary before cooling and falling back. This overshoot helps mix elements inside the star. It can pull fresh hydrogen downward and lift heavier elements upward. Over centuries, this mixing alters the star's composition and influences future stages of evolution. You could picture overshoot as tossing a ball high into the air. Even after the force stops, the ball continues upward briefly before slowing and dropping. Inside Betelgeuse, the ball is a chunk of glowing plasma, and the air is a region where the temperature and density change abruptly. Shock waves also ripple through these layers. They originate where burning shells fluctuate in temperature and pressure. When a shell brightens suddenly, it sends a wave expanding outward. These waves aren't explosive, just firm pulses of pressure. When they reach the outer layers, they contribute to the surface wobble we see as brightness variation. Spectroscopic studies reveal these shocks through line broadening. Spectral lines smear slightly when gas moves at different speeds along the line of sight. Scientists at observatories around the world collect these spectra, stacking them night after night. They look for subtle shifts in the H-alpha line, the titanium oxide bands, or the near-infrared features. Every shift tells them something about motion deep inside the star. You imagine one of these scientists adjusting the spectrograph, tightening screws, and checking calibration lamps before the night begins. They sip coffee under dim red lights, waiting for Betelgeuse to rise. When the star appears, they take exposures, each one capturing a tiny hint of the star's internal turbulence. Inside the intermediate layers, immense vortices form, spiraling flows of plasma that swirl like giant whirlpools. These vortices can last months or even years. They redistribute heat and influence the frequencies of the star's pulsations. And when they interact with other currents, they can generate chaotic behavior, adding complexity to the star's already unstable rhythm. Thinking about these vortices might remind you of watching eddies in a slow-moving river. Leaves swirl in circular paths, drawn into quiet whirlpools that linger even as the river flows past. Inside Betelgeuse, the plasma behaves in a similar way, swirling, circling, sometimes merging, sometimes breaking apart. The density of the plasma increases dramatically as you move inward. Near the surface, it's extremely low, comparable to a vacuum chamber. But deeper within, the density rises until it becomes thicker than any earthly substance can withstand. It's still plasma, still fluid, but with a weight that defies intuition. You might imagine it as liquid metal, flowing in slow-motion tides. When astronomers simulate these layers, they use 3D hydrodynamic models. These models run on supercomputers and require enormous processing power. Turbulence alone is so computationally expensive that they simplify some parts. Even then, the simulations sometimes crash. Researchers might spend days debugging, only to realize the physics they're modeling is too unstable to converge easily. Betelgeuse is simply that chaotic. The middle layers also harbor the seeds of future instability. As the core contracts further in the coming tens of thousands of years, the temperatures will rise. Carbon will eventually ignite in the core or in shells. When that happens, the internal structure will change drastically. These layers will become more turbulent, their motions more violent. But right now, the star is in a delicate balance. Energy rises slowly. Plasma circulates. Pulsations stretch and contract the layers. Each motion contributes to the star's overall behavior. From far away, Betelgeuse appears calm, like a steady red point in the night. Up close, it's alive with movement. You lying there in the quiet, listening to this might feel a kind of kinship with this instability. Your own thoughts rise and fall, warm and cool, swirl and settle. The star's inner churn mirrors the complexity of a human mind, unpredictable, layered, full of motion that others cannot see. And as Betelgeuse continues to pulse and shift, you drift a little deeper into the story of this dying giant, ready to follow the next thread of what is unfolding inside it. As you drift outward from the middle layers of Betelgeuse, the star begins to feel strangely fragile, as if the outer atmosphere is less a surface and more a thin veil trying to hold itself together. These regions are vast, diffuse, and trembling, places where gravity struggles to keep material from drifting away. You picture yourself floating through the reddish haze, watching tiny grains of dust forming before your eyes. In these external layers, temperatures drop drastically compared to the interior. Here, the plasma cools enough for molecules to begin forming: titanium oxide, silicon monoxide, carbon-rich compounds. At just the right temperature range, these compounds condense into dust. The dust forms in clumps, arcs, and irregular shells that drift outward like slow-moving smoke. Every piece of dust came from deep within the star. Scientists estimate that Betelgeuse loses material at a rate of roughly 1 Earth mass every year. Over long periods, this becomes enormous, entire solar masses over hundreds of thousands of years. The star's outer layers are leaking into space, creating a giant inky, expanding envelope of gas and dust that surrounds it like a faint aura. You imagine drifting inside that envelope. It feels like moving through a dim, glowing fog. Tiny particles shimmer as they catch the light. They're warm at first, but as they drift farther from the star, they cool rapidly. Some clumps collapse into dense patches. Others stretch into long, filament-like shapes that trail behind the star's slow wind. Observations from ALMA revealed these structures in incredible detail. Astronomers using the array mapped out the star's outflows in sub-millimeter wavelengths, discovering arcs, knots, and asymmetric shells. Instead of a smooth, spherical wind, the material escapes unevenly. Some regions show strong bursts, others barely lose anything. Betelgeuse is shedding itself in uneven breaths. The ALMA panels used in these observations are vast. 66 antennas spread across the Atacama Desert. Each must be calibrated, aligned, and synchronized through precise timing signals. Technicians walk between them tightening bolts, cleaning protective covers, and checking electronics while scientists inside control rooms monitor the data stream. Bit by bit, an image forms, a lopsided halo around a trembling giant. One of the most intriguing findings from ALMA is the presence of high-velocity clumps moving outward faster than expected. These clumps may be connected to giant convective plumes that erupted from the star's surface. When a plume bursts upward, it can carry material into cooler regions where dust forms rapidly. This process may explain sudden changes in brightness, like the Great Dimming in 2019. Imagine one of these eruptions occurring beneath you. A huge pocket of gas expands upward, stretching the star's atmosphere like a slow balloon. The gas cools, condenses into dust, and forms a cloud that partially blocks the light. From Earth, the star appears to fade. Up close, the scene looks like a red mist being exhaled into the void. These external layers also contain shock waves created by pulsation cycles. When the star contracts, pressure builds inside and then bursts outward as it expands again. These pressure bursts push material away from the star, fueling the uneven wind. This wind can reach speeds of tens of kilometers per second, fast enough to escape the star's weak surface gravity. Spectroscopic observations have revealed these wind speeds through Doppler shifts in specific molecular bands. Scientists track the motion by analyzing tiny shifts in wavelength. A slight blue shift indicates material moving toward us. A red shift indicates material moving away. By mapping these shifts across the star, researchers can reconstruct the 3D flow of gases. You imagine a researcher staring at a graph filled with peaks and valleys. Each peak represents the velocity of gas moving in one direction. The lines are thin, delicate, easily distorted by noise or atmospheric interference. They study the curves, squinting at a barely visible dip, wondering if it's a real feature of Betelgeuse or a flaw in the detector. Farther out, where the star's influence weakens, the dust begins forming arcs and shell-like structures. These structures record past eruptions, each layer representing a moment when the star expelled material. Over thousands of years, these layers expand outward, forming a cosmic fossil record of Betelgeuse's instability. These arcs are often compared to rings in a tree trunk, but unlike a tree, Betelgeuse's rings aren't evenly spaced. Some are thick, evidence of strong eruptions, others are faint. The star doesn't age gracefully. It spasms its material outward in bursts that grow clumsier as the core contracts further. You drift through one of these arcs. The dust brushes past you like fine ash. Little by little, the particles thin until you can see the faint shimmer of the star behind you. The arc glows softly, illuminated by light that left the star centuries ago. The whole structure feels like a ghost of something once burning brightly. Another interesting feature of Betelgeuse's outer layers is the presence of chaotic magnetic fields. Although Betelgeuse is not strongly magnetic like some stars, its turbulent surface generates weak magnetic structures. These fields may help channel material outward, shaping the asymmetric wind. The existence of these magnetic fields was detected through polarimetric measurements, techniques that examine how light becomes polarized as it interacts with magnetic regions. The signals are faint, barely above noise level. But repeated observations reveal consistent trends. Betelgeuse is magnetically restless. You picture the scientists gathering polarimetric data, using sensitive instruments that must be shielded from even minor vibrations. One bump on the observing platform could ruin an exposure. They sit quietly waiting for the data to accumulate, knowing that each photon collected helps map something invisible. The outer layers also contain molecules that form only under very specific conditions. Some of these molecules, like silicon monoxide, emit radiation at precise frequencies. These emissions let astronomers map the temperature and density of the surrounding gas. When ALMA detects these emissions, it shows exactly where the gas is thickest or coolest. These molecules act like cosmic thermometers. By reading their signals, scientists determine how recently the material was ejected. Newer material is hotter and denser. Older material is more diffuse. In this way, the entire envelope of Betelgeuse becomes a timeline of its last centuries. You lying there in the dark might picture this envelope as a giant, dusty cloud slowly expanding around a fading ember. Each layer drifts outward, carrying with it the memory of the star's internal struggles. It's a soft kind of unraveling, one that happens so slowly that no single moment looks dramatic unless you step back and see the whole picture. And as Betelgeuse continues to shed itself into space, you drift deeper into its story, following the fragile threads that lead from the trembling surface into the vast, cooling halo beyond. You let yourself hover just above the outer layers you've been exploring, when something faint catches your attention, subtle ripples passing through the star, like distant tremors moving through a landscape. They're slow and quiet, yet they reshape everything. These are the internal waves of Betelgeuse, and they're happening constantly, pulsing through the star's enormous body in patterns older than recorded history. These waves are produced by the imbalance between pressure and gravity. Every time the star expands or contracts, it creates oscillations that travel inward and outward, shaking the interior like a struck instrument. Unlike on Earth, where waves travel through rock or water, here they move through plasma, charged, turbulent, unstable. The physics is the same, but the scale is unimaginable. Scientists call these movements modes of oscillation. Some are radial, waves that move straight in and out, like a balloon inflating and deflating. Others are non-radial, sliding around the star's surface like ripples across a pond. Betelgeuse hosts dozens of such modes, all interacting, amplifying, and cancelling each other in a constant dance of instability. In these oscillations lies part of the reason Betelgeuse's brightness flickers so unpredictably. When an outward moving wave aligns with a convection plume, the surface brightens. When they collide destructively, the brightness dims. The star is a luminous symphony of overlapping rhythms, each one slightly out of sync with the others. Imagine placing your hand on Betelgeuse's surface, not to feel heat, because heat here is unimaginable, but to sense vibration. The star would tremble like the skin of a drum touched lightly by wind. Every shiver would be a message from deep inside, a record of the star's changing heart. Asteroseismology, the study of stellar vibrations, helps scientists interpret these tremors. They analyzed tiny brightness changes, using them like fingerprints. Each oscillation mode corresponds to a different internal structure. The data looks like noisy scatter plots at first, the kind of mess that makes researchers squint at graphs for hours. But within the noise are patterns. Some teams working with these light curves fill whiteboards with sketches of predicted frequencies. They discuss scaling relations, density profiles, energy transport. They theorize which modes Betelgeuse might host and how they would appear from Earth. It's half physics, half intuition, an attempt to listen to a star. One of the most important modes inside Betelgeuse is the fundamental radial mode, where the star expands and contracts in unison. This is the heartbeat that dominates its long-period oscillations, especially the 400-day cycle observed by multiple teams. Higher order modes create smaller, quicker pulses layered on top. You picture these modes as threads woven through the star. Some threads stretch and tighten as the star contracts. Others loosen when the star expands. Together they form a tapestry of motion, a pattern repeating, shifting, echoing across centuries. Another type of wave, the gravity mode, travels along regions where buoyancy forces dominate. These waves are common in deep stellar interiors, but difficult to observe directly. In Betelgeuse, some models suggest they may interact with convective plumes, altering their timing and shape. It's like watching ocean tides change the behavior of passing waves. You might imagine floating in an enormous, glowing ocean inside the star, watching these slow ripples drift past you. They move silently, carrying the story of the core's gradual contraction and the outer layer's fragile expansion. Nothing is still. Everything sways. Evidence for these waves appears in subtle shifts in spectral lines, tiny wiggles in the data that require high precision to detect. Observatories dedicated to long-term monitoring gather these measurements night after night. They rely on stability, stable instruments, stable weather, stable calibration lamps. Yet the star they're watching is anything but stable. Researchers often talk about Betelgeuse with a mix of affection and frustration. Its variability makes clean data difficult. On some nights, atmospheric turbulence ruins everything. On others, the star's erratic surface activity introduces unexpected noise. But these frustrations only deepen the fascination. Betelgeuse behaves like a living thing with moods. If you could hear Betelgeuse instead of see it, the sound would be strange. A low, slow hum, perhaps, layered with long rumbles and gentle pulses. Not music exactly, but a resonance, a breathing, a deep, ancient rhythm forged in helium-burning flames. Waves inside Betelgeuse don't simply reflect the star's current state, they foreshadow its future. As the core contracts more rapidly in the coming millennia, the frequencies of these modes will shift. Some modes will strengthen, others will disappear. Asteroseismologists model these shifts to estimate how close Betelgeuse is to core collapse. But interpreting these models isn't easy. Betelgeuse doesn't match the simple equations used for stable stars. Its enormous radius, its intense convection, its irregular outflows, all add complexity. Sometimes, the star behaves like it's heavier than expected. Other times, like it's lighter. It keeps its secrets well. You lying in your quiet room may feel an unexpected resonance with this unpredictability. Humans, too, shift in ways impossible to graph neatly. Some days, steady, others, restless. Betelgeuse reminds you that not everything in the universe follows smooth curves. The star's oscillations also reveal regions where pressure waves and gravity waves interact, creating mixed modes. These hybrid waves carry information from both the core and the envelope, making them valuable but hard to interpret. They hint at boundaries between burning shells, gradients in density, transitions that would otherwise remain hidden. Imagine drifting near one of these boundaries. You feel the texture of the plasma change, a gentle tug in one direction, a soft pull in another. The wave passing through is neither purely upward nor purely sideways. It meanders, tracing invisible layers before dispersing into warmth. Betelgeuse currently sits in a state where several oscillation modes compete for dominance. Some models suggest the star may be in a transitional phase where new modes emerge as the core heats. These transitions cause irregular behavior, such as the long secondary period, a mysterious brightness cycle that lacks a clear physical explanation. Scientists propose theories: strange convection coupling, global flow patterns, or even slow internal rotation. They argue politely at conferences, drawing diagrams on napkins, pointing to data on laptops, each one convinced of a different interpretation. Betelgeuse invites debate. You imagine one such conversation taking place on a cold observatory night. Two researchers stand by a railing, looking at the Orion constellation overhead. One gestures toward Betelgeuse, trying to explain a new oscillation model. The other shakes their head, unconvinced. Their breath fogs in the cold air, drifting upward toward the very star they're discussing. In a poetic sense, Betelgeuse behaves like a memory that flickers, sometimes bright, sometimes dim, never perfectly consistent. Its internal waves are like emotion rising through layers of a human heart. Warm, chaotic, sometimes conflicted. Not everything needs to be stable to be meaningful. And as these waves continue their slow journey through the star, something subtle begins to gather beneath them. Another phenomenon, quieter and deeper, shaping the star's evolution in ways that will take you somewhere even stranger. As you drift mentally through Betelgeuse's trembling atmosphere, something more subtle than convection begins to reveal itself. An immense, slow twist running through the star. It's rotation, but not the gentle, orderly spin of smaller stars. Here, rotation is stretched, distorted, uneven. You sense it like a slow spiral beneath your feet, as though the entire star is turning in a way that struggles to remember its original rhythm. Betelgeuse spins shockingly slowly at the surface, roughly 5 kilometers at the equator, far slower than massive stars typically do. But the interior tells a different story. Models indicate that deep layers rotate faster than the outer envelope. This difference creates shear zones, regions where adjacent layers move at slightly different speeds. These zones twist and pull on the plasma, amplifying turbulence and contributing to the star's unpredictability. Rotation affects nearly everything happening inside the star. It shapes convection cells, warps oscillation modes, and even influences how material is ejected from the surface. When the interior rotates faster, it drags some currents along with it, tilting them. When the surface lags behind, these currents stretch, forming spiraling structures. Betelgeuse is not a uniformly spinning sphere. It's a tangled web of rotating shells. You imagine drifting through one of these shear regions. The flow around you doesn't travel in one direction. It slides, twists, and shifts like overlapping currents beneath an ocean surface. There's no clear path, only a feeling that everything rotates with a kind of exhausted determination, as though the star is trying to maintain an identity long after its structure has weakened. Astronomers estimate Betelgeuse's rotation using spectroscopy. By analyzing the broadening of spectral lines, they infer how fast the star's surface rotates along our line of sight. These measurements are difficult because the star's surface is uneven, patchy, and constantly shifting. The rotational signature becomes tangled with pulsation-induced motion, making it tricky to isolate the true spin. Researchers often debate these rotation values. Some argue Betelgeuse rotated much faster earlier in life and has slowed dramatically due to mass loss. Others suggest binary interactions may have influenced its spin. Papers are written proposing different angular momentum histories, all built on data that must be carefully extracted from noisy, complex spectra. The star's rotation interacts with its weak magnetic field as well. As plasma moves across magnetic structures, it stretches and distorts them. Simple loops become chaotic filaments. These magnetic irregularities don't dominate the star's behavior, but they nudge it, slightly altering how material is lifted from the surface or how waves propagate through outer layers. You might imagine these magnetic structures as faint threads drifting through a storm. They don't control the winds, but they influence how droplets swirl, how gusts bend, how the entire storm subtly shifts. Inside Betelgeuse, the same thing happens, just on scales so large they defy easy intuition. Polarimetric measurements have detected small but consistent magnetic signatures in Betelgeuse's light. These signatures appear as tiny asymmetries, barely above noise level. Extracting them requires meticulous processing, subtracting instrumental effects, compensating for atmospheric polarization, and verifying that the signal is not an artifact. But after dozens of nights of data, the magnetic fingerprint emerges. The scientists who detect these signals work in dim control rooms, adjusting sensitivity thresholds, running calibration sequences, and checking for tiny drifts in their instruments. Each new detection is celebrated quietly, often with tired smiles. They know they're seeing something fragile and real from a star hundreds of light years away. Rotation also affects Betelgeuse's mass loss. Faster-moving regions fling material outward more easily. Slower regions hold onto it longer. This contributes to the star's asymmetric outflows, those strange arcs and clumps observed by ALMA and the VLT. Some parts of the star lose mass in gusts, others barely leak anything. If you drifted above one of these rotationally active zones, you might see the surface bulge subtly, an uneven, rising region where plasma is lifted just enough to escape. It doesn't look like an eruption, but more like a slow exhalation. The rotation just nudges things along. Another effect of rotation is the star's slight ablateness. Betelgeuse isn't perfectly round. The equator bulges a bit due to centrifugal force. The difference is small but real. Interferometric imaging shows subtle elongation, a kind of asymmetry that adds another layer to the star's complexity. This ablateness subtly modifies oscillation modes. Waves traveling around the star's surface don't take identical paths. Some move around the bulged equator. Others travel toward the slightly compressed poles. These differences change their frequencies and patterns, contributing to the star's irregular pulsations. You might imagine walking around a lake whose shoreline is uneven. Some paths take longer than others. Some slope gently upward, others dip. The lake's shape determines your journey. In Betelgeuse, the star's shape determines how waves travel, how pulses spread, and how brightness shifts over time. Internal rotation also influences the mixing of elements. Faster rotation can drag heavier elements upward or pull lighter ones downward. Over thousands of years, this mixing affects the star's chemical profile. Observations of specific spectral lines, such as those from carbon, nitrogen, and oxygen, show signs that Betelgeuse has undergone strong internal mixing. This mixing is like stirring a giant pot of glowing soup. Ingredients don't stay in neat layers. They swirl, blend, rise, and sink. The result is a star whose outer layers contain elements that should be deeper within, evidence of a dynamic, changing interior. As Betelgeuse evolves, rotation will continue slowing. Mass loss steals angular momentum. The outer layers expand, reducing rotational speed further. In time, the star may become almost motionless at the surface while the core continues rotating faster. An internal tension that will never fully resolve before collapse. You lying in your quiet space might find something strangely comforting in this. Even stars carry internal contradictions, fast and slow, stable and unstable, rising and falling. They are not static symbols in the sky. They are shifting, struggling structures moving toward an inevitable end. And somewhere within this slow, uneven spin, a deeper and even more delicate process is unfolding, one that shapes how the star breathes, brightens, dims, and prepares for the chapters yet to come. When you imagine drifting upward inside Betelgeuse, you eventually reach a strange frontier. Its photosphere, the closest thing this star has to a surface. But nothing about it resembles a solid boundary. Instead, it feels like approaching a glowing fog, a layer where light you eventually see escapes after bouncing around inside the star for thousands of years. You hover there, sensing the texture of something that is neither firm nor empty, but alive with motion. This photosphere is cooler than the layers beneath it, only a few thousand degrees Kelvin. At these temperatures, molecules can form briefly before being torn apart again. Titanium oxide, carbon monoxide, and water vapor exist fleetingly, shaping the star's spectrum. These molecules absorb and emit light in ways that cause the star's brightness and color to shift slightly from night to night. The photosphere isn't smooth, it's mottled with bright spots, dark patches, and irregular arcs. These structures reflect deeper currents, convection plumes rising, cooler pockets sinking, shockwaves passing. In some regions, the photosphere bulges outward by millions of kilometers. In others, it sinks slightly, pulled inward by denser pockets of plasma. The entire layer resembles a restless sea. You imagine placing your hand at the edge of this photosphere, watching glowing eddies drift past like slow embers. Some swirl upward, others fade. Each movement carries the signature of something deeper, a pulse from the core, a rotating plume, a shockwave that took months to reach the surface. Betelgeuse's outer skin is a mirror of its inner chaos. Interferometric imaging from the Very Large Telescope has revealed astonishing details of this surface. In some images, one hemisphere appears brighter than the other. In others, a huge dark patch dominates a quadrant. These features shift over months, causing Betelgeuse to flicker subtly when viewed from Earth. To astronomers, these irregular shapes are clues in a complex riddle. Scientists who work with interferometric data often spend nights aligning mirrors, checking baseline lengths, and correcting for atmospheric turbulence. The raw data looks like ripples, fringes, circles, and shadows, patterns only computers can interpret. After dozens of reconstruction attempts, a coherent image emerges, showing Betelgeuse as a misshapen, uneven sphere. These reconstructions revealed that during the 2019 Great Dimming, one region of the photosphere cooled significantly. This cooling allowed dust to form just above the surface. The dust cloud partially blocked the star's light, causing the dramatic brightness drop. It wasn't a death throw, it was a cloud passing in front of a restless flame. You picture this dust forming in real time. Tiny grains condense in the cooling pocket, forming a patch of dark smoke drifting outward. The star behind it still burns fiercely, but the cloud dims the view, like watching a campfire behind fogged glass. The effect is temporary, but striking. These dust-forming zones appear irregularly. Sometimes two form at once, sometimes none. The randomness reflects the star's deep asymmetry. Where a plume erupts, dust follows. Where a shockwave compresses material, dust rapidly condenses. Betelgeuse is creating and destroying its own veil constantly. ALMA observations revealed that dust doesn't form uniformly. Clumps of carbon-rich dust drift outward at different speeds, suggesting that the star's wind isn't a steady stream but a patchwork of gusts. Each gust carries material that once belonged to Betelgeuse. Each particle drifting outward is a fragment of the star's long and slow unraveling. Imagine drifting through one of these clumps, The grains glow faintly from infrared radiation. They slide past in silence, like glowing pollen drifting through warm air. You feel suspended in a cloud made of stardust, material that might someday become part of a planet or moon around a future star. Dust formation depends heavily on temperature gradients. Regions that cool just slightly can become dust factories. Warmer regions remain too chaotic. This creates a patchy structure. Some parts of Betelgeuse look smooth, others grainy or blotched. The star's surface is never uniform for long. Spectral signatures of silicon monoxide masses reveal swirling structures above the photosphere. Masers, microwave amplification by stimulated emission, occur when molecules are excited and begin emitting at specific frequencies. These emissions help scientists map motions in the extended atmosphere. The patterns often show spirals, arcs, or clumps rising then fading. Observatories equipped for maser detection run delicate instruments. Technicians adjust cryogenic cooling systems to keep detectors at ultra-low temperatures, ensuring maximum sensitivity. A small temperature drift could blur the signals. When the masers finally appear on the screen, thin, bright streaks, they reveal swirling motions invisible to the naked eye. Betelgeuse's extended atmosphere is so large that Earth's orbit would fit comfortably inside it. Floating there in imagination, you might feel as though you're wandering through a sky filled with warm, glowing fog. Gravity is weak, light scatters, and every layer feels loose, like everything is one exhale away from drifting into space. These upper regions behave like a buffer between the star and the surrounding interstellar medium. Shock waves from pulsations travel through this extended atmosphere, compressing and stretching it. Some waves push dust outward, others collapse regions inward, creating temporary pockets of density. The photosphere also hosts temperature fluctuations of hundreds of degrees. Hotter regions appear brighter and often correlate with rising plumes. Cooler regions appear darker, sometimes marking the beginnings of dust formation. These fluctuations happen over weeks or months, creating slow shifts in the star's appearance. You might picture these fluctuations as patches of glowing fabric, drifting and reshaping themselves. The brighter patches throb gently, the darker ones contract. It's like watching a giant lantern with an uneven flame flickering behind stretched cloth. The flicker is slow but mesmerizing. Magnetic fields within the photosphere are weak but present. They slightly influence how dust forms, guiding charged particles. These fields may also shape small-scale structures, contributing to the asymmetries seen in images. They're subtle forces, threads tugging gently at the star's outer veil. Despite all this complexity, Betelgeuse remains surprisingly stable over long timescales. It isn't in immediate danger of collapse. The slow shedding, the dimming events, the turbulence, they are natural phases of a massive star's late life. Betelgeuse is unsteady but not failing. Not yet. You lying in your quiet room might feel something unexpected in all this. Even apparent instability can have its own kind of order. Betelgeuse wavers because it's alive with processes too large and slow for human senses. What looks chaotic from outside is simply the rhythm of a giant nearing its final chapters. And as this glowing atmosphere continues to stretch and ripple, something deeper waits beneath it, a sign that Betelgeuse's interior is preparing for a shift far more dramatic than these drifting clouds suggest. As you drift outward from Betelgeuse's trembling photosphere, the light softens and the air feels thinner, as if the star's grip is fading. The reddish glow behind you becomes diffused, scattered by a vast cloud of gas and dust that surrounds the star like a slowly expanding cocoon. This region is colder, quieter, and strangely serene, yet every grain, every molecule drifting here was once part of Betelgeuse's body. Temperatures in this envelope can fall to a few hundred Kelvin. Molecules such as carbon monoxide, silicon monoxide, and ammonia survive here, floating through the star's extended atmosphere. These molecules trace arcs, loops, and faint spirals, preserved in slow motion as the star continues shedding its mass. Some regions are denser than others, forming ghost-like structures that drift centimeters per second across astronomical distances. Observations from the Herschel Space Observatory revealed something extraordinary. Betelgeuse's stellar wind, its continuous exhalation of gas, slams into the surrounding interstellar medium, forming a bow shock. This bow shock appears as a curved arc ahead of the star's motion through space. Betelgeuse is plowing through the galaxy, leaving behind a trail of material and compressing the gas in front of it like the prow of a ship cutting through water. You imagine drifting far enough away to see this bow shock clearly. It stretches across space like a faint glowing shield. Dust and gas pile up where Betelgeuse's wind meets the thin interstellar medium. The boundary glows in infrared wavelengths, heat left over from millions of tiny collisions. The star carves its own path through the galaxy, and you can sense that movement as a slow push beneath your feet. The Herschel images show at least 2 arcs, evidence that Betelgeuse went through different phases of mass loss. One arc is closer, from recent ejections, another lies farther out, from older eruptions. These arcs act like tree rings, recording the star's history in layers of drifting dust. They show times when Betelgeuse exhaled more strongly, times when it barely breathed at all. Scientists studying these arcs work with data from far infrared detectors that collect faint thermal signals. They calibrate the images, correct for cosmic rays that strike the sensors, adjust for artifacts from the spacecraft's motion, and then combine dozens of exposures. The result is a delicate glow surrounding Betelgeuse, its signature written across space. Closer to the star, the gas moves at roughly 10-20 kilometers, expanding outward in irregular waves. As it cools, the gas forms clumps, some thick, others filament-like. Alma mapped these clumps in exquisite detail, showing that Betelgeuse's wind is not a gentle breeze, but a chaotic, uneven gale. Some regions spew gas violently, others remain quiet for years. You picture drifting through one of these clumps. The dust glows faintly from Betelgeuse's infrared emission. As you move, the particles swirl around your presence, like motes drifting through warm sunlight. These particles may someday join the interstellar medium, becoming seeds of future stars or planets long after Betelgeuse has collapsed. The bow shock also contains extremely cold regions, pockets at just a few tens of Kelvin. In these cold pockets, complex molecules can form. Astronomers have detected signatures of carbon-bearing molecules that shouldn't exist so close to such a hot star, suggesting that Betelgeuse's winds undergo rapid chemical transitions as they expand and cool. This chemistry is pieced together through radio and submillimeter spectroscopy. Scientists analyze specific spectral lines, identifying molecules by their unique rotational transitions. Each molecule emits at a particular frequency. When these signals appear, researchers circle them excitedly, knowing they reveal the star's long-distance fingerprints. Farther out, dust grains begin interacting with the galactic magnetic field. They align slowly, creating weak polarization in the infrared light that passes through. Instruments aboard space telescopes detect this polarization, helping astronomers map the structure of the interstellar magnetic field in Betelgeuse's neighborhood. Even dying stars help reveal the galaxy's skeleton. You imagine watching these grains align. It's like seeing tiny leaves orient themselves in a faint breeze. Individually, each grain seems insignificant. Together, they create a pattern, a whisper of the magnetic forces threading through the Milky Way. The envelope around Betelgeuse extends several light years. This means light leaving the star tonight must travel through layers of dust and gas ejected centuries earlier. When you look at Betelgeuse in the night sky, you are not only seeing a star, you are seeing a star surrounded by the echoes of its own past. This surrounding cloud also influences the star's appearance. Dust can scatter or absorb light, causing the star to appear slightly redder or dimmer at times. Some scattering events are predictable, others are chaotic, tied to recent eruptions. Betelgeuse's weather extends far beyond its photosphere. Imagine drifting through a region where the dust thins, revealing a faint window back to the star. Its red-orange glow flickers through gaps in the cloud. Through those shifting glimpses, the star feels more fragile, as though its outer layers are unraveling thread by thread into the surrounding dark. The bow shock ahead of Betelgeuse isn't static. Models suggest that as the star continues to lose mass, the shape of the shock shifts. The arc may stretch, it may split, it may form new layers. Each change reflects ongoing battles between the star's weakening wind and the galaxy's thin, cold gas pressing against it. Researchers simulate these interactions using hydrodynamic models. They input mass loss rates, wind velocities, interstellar gas densities. After hours of computation, the simulations show arcs forming, thickening, stretching. Some simulations resemble Herschel's images exactly. Others diverge wildly, prompting teams to tweak parameters again. This envelope and bow shock aren't just scenery, they are Betelgeuse's autobiography, written across space. Every ripple, every patch of dust, every arc carries a memory of something the star endured. A strong pulse, a cooling event, a burst of mass loss. You're drifting through the star's diary, one written not in ink, but in drifting particles. You lying there in a quiet room might find something unexpectedly peaceful in this idea. Even a star's turmoil can leave behind beauty, glowing arcs, drifting dust, structures shaped not by perfection but by instability. Stars don't hide their flaws. They scatter them across light years. And somewhere beyond these drifting layers, farther from the warmth and turbulence, something even more delicate is forming, something that carries the first quiet hints of the star's eventual fate. As you drift farther from the envelope and begin looking back toward the starry, something subtle becomes clearer. Beneath all the swelling, shedding, trembling, and glowing, Betelgeuse is carrying a secret. Its core is changing faster than the outer layers reveal. You sense a deep heaviness below the surface, like an old furnace burning hotter and smaller at the same time. The star doesn't show this openly, but the clues are there if you know how to look. Deep inside, the helium-burning core is contracting gradually. As it contracts, it heats. And as it heats, it begins preparing for the next stage of stellar burning, one that will eventually ignite carbon. Betelgeuse isn't burning carbon yet, but the conditions are shifting in that direction. Rising core density, increasing temperature, growing imbalance between gravity and pressure. The star knows what is coming long before anyone watching from Earth can see it. Temperatures in the core exceed 100 million degrees. The density is high enough that electrons begin resisting further compression, creating electron degeneracy pressure. This pressure keeps the core from collapsing, for now. But as the helium supply dwindles, the degeneracy strengthens, the core shrinks more rapidly, and the outer layers respond by swelling and trembling. Every pulse you've imagined so far is a symptom of that deeper contraction. Scientists infer these core changes not through direct measurement, but through models calibrated by surface observations. They track the star's pulsation periods, brightness cycles, and spectral signatures. When the interior reorganizes itself, those external signs shift slightly. Tiny changes in the long secondary period, in the amplitude of pulsations, or in temperature variations all hint that the core is stepping toward its next evolutionary phase. You imagine these signs as soft whispers rising from the star's interior, barely audible but persistent. A slight slowing here, a faint strengthening there. Betelgeuse isn't shouting its future, it's murmuring it, and astronomers have learned how to listen. One of the key indicators of approaching transitions is the star's mass loss pattern. As the core contracts, the outer layers become easier for the star to shed. Observations show Betelgeuse losing mass at a rate comparable to other late-stage red supergiants, but the pattern is changing, more asymmetric, more clumpy. ALMA images show distinct outbursts spaced irregularly, hinting at internal events that trigger them. Researchers compare these ALMA maps with hydrodynamic models of stars nearing carbon ignition. They look for matching patterns, wave-like eruptions, uneven mass ejections, density gradients. Many of the simulations show behavior remarkably similar to Betelgeuse today. It's a sign that the star might be approaching the later phases of helium burning. Another clue lies in the pulsation modes. As the core contracts, the frequencies of certain oscillations shift. The fundamental radial mode may lengthen slightly. Higher-order modes may appear or disappear. This mode-changing behavior is characteristic of stars transitioning between burning stages. When astronomers track these shifts, they see Betelgeuse's internal rhythm gradually evolving. You can imagine these oscillations as the changing tempo of a drum being tightened. As the drumhead stretches, the pitch rises. As Betelgeuse's core contracts, its pitch shifts. The star's atmosphere becomes the surface of that drum, trembling in response. Inside the core, helium fusion still dominates, but the helium supply is slowly depleting. Above the core, hydrogen continues burning in a shell. The combined effect of these two burning shells is instability. Shell burning is inherently uneven. It flares and fades, creating pulses of heat that travel outward. These pulses are thought to contribute to some of Betelgeuse's irregular variability. When shell burning intensifies, the star swells. When it weakens, gravity takes hold, and the star contracts slightly. This expansion-contraction cycle will continue until the core reaches conditions necessary for the next fusion stage. That stage will be short-lived compared to the millions of years Betelgeuse spent burning hydrogen and helium. One of the most mysterious signs comes from changes in Betelgeuse's brightness curves recorded over the past decades. Although the brightness has always fluctuated, some recent fluctuations appear slightly larger or more asymmetric than those from earlier years. It's subtle, so subtle that researchers debate whether it's meaningful. But subtlety is often where stellar evolution hides its earliest clues. To analyze these patterns, scientists compare recent photometric data with historical records, some going back more than a century. They digitize old observations, cross-check with modern measurements, and run statistical tests. The curves wiggle and drift. Some features repeat, others vanish. Betelgeuse feels like it's trying to say something in a language of flickers. You imagine a researcher hunched over a monitor, overlaying brightness curves from different decades. One curve rises slightly faster than expected, another dips at an unusual time. The differences are tiny but intriguing. They hint at something shifting deep inside the star, a quiet rearrangement rather than a dramatic rupture. Another crucial sign is the rate of neutrino production. During helium burning, neutrino output is moderate, but as temperatures rise, even before carbon ignition, neutrino emission increases. These neutrinos escape almost instantly, carrying energy directly from the core. Humans don't currently have instruments sensitive enough to detect these neutrinos from Betelgeuse, but models estimate a gradual increase in their production as the star approaches later burning stages. The idea of limitless neutrinos streaming out of the core is almost poetic. These ghost-like particles pass through everything, through the star, through space, through you as you lie listening. They are silent witnesses to processes no telescope can see. Rotation also affects the star's evolutionary future. If the core rotates faster than the envelope, angular momentum is transferred unevenly. This can influence how the burning shells interact and how quickly the core heats. Some models suggest that Betelgeuse's internal rotation may accelerate the timeline of the next evolutionary stage slightly. You might picture the core as a slowly tightening spring, winding down toward a moment when it snaps into a new state of fusion. The star doesn't rush, it shifts gradually, with each contraction bringing it closer to the threshold. Despite these gradual changes, Betelgeuse is not on the brink of collapse. It could take tens of thousands of years before the star enters carbon burning. The popular idea that Betelgeuse might supernova any day now is more poetic than scientific. The star is evolving, yes, but cosmic evolution moves at a pace that makes human anxieties seem brief and fleeting. Reflecting on this, you might feel the scale of time stretching gently around you. The star is changing, but slowly. You're witnessing a single breath in its long, unsteady life. And yet, even slow changes can reveal something profound about the nature of instability and transformation. And somewhere beneath all these signs, beneath the drifting dust, the trembling photosphere, the swirling convection, something deeper is gathering momentum, preparing for the next chapter in the star's long, glowing unraveling, waiting quietly in the core's tightening heat. As you drift in your imagination back toward the star, feeling its light shimmer through the drifting dust, a deeper question settles in. What happens next? Not tonight, not next year, not even in your lifetime, but in the quiet, inevitable direction this giant is moving. Betelgeuse isn't dying in a dramatic collapse you can see. It's dying the way mountains erode, slowly, irregularly, invisibly from the surface. But its interior already carries the signatures of what it will someday become. The next major milestone in Betelgeuse's evolution will be carbon ignition. But that moment is still far away, thousands, perhaps tens of thousands of years. Before carbon burning begins, the core will continue shrinking, heating, and becoming more degenerate. The shells around it will grow more unstable. Pulsations will likely become slightly stronger. The tremors you've been drifting through these past chapters are not the end. They're the beginning of a long preparation. To ignite carbon, temperatures must exceed roughly 600 million degrees. That number is staggering, but it's the natural progression of fusion in massive stars. Each stage requires more heat, more pressure, more contraction. Betelgeuse is climbing that ladder slowly, step by heavy step. The signs we observe now, erratic pulsations, intensified mass loss, subtle shifts in oscillation frequencies, are faint hints that the core is inching toward that threshold. You might imagine this as the star tightening inward. The outer layers puff and relax, but the core only shrinks, only warms, only moves forward. There is no reverse gear at this late stage of evolution. Gravity pushes, fusion responds. And step by step, Betelgeuse approaches the moment when it will no longer have fuel capable of balancing its own weight. Astronomers model these transitions using codes like MESA, which simulate nuclear burning, mass loss, mixing, and rotation. When they adjust parameters to match Betelgeuse's observed size, temperatures, and luminosity, most models place the star firmly in late helium burning. That means carbon burning is next, but the timetable is fuzzy. Small uncertainties in mass or mixing efficiency expand the timeline by thousands of years. Stellar evolution is precise physics, but with uncertain clocks. You picture a researcher watching a simulation finish after hours of computation. The core temperature graph rises gently, the radius oscillates, the luminosity curve shifts. None of it screams supernova soon. Instead, it whispers supernova someday, and the scientist leans back in their chair, accepting the slow inevitability. When carbon burning does eventually begin, the star will enter a rapid sequence of fusion stages. Carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron. These stages are brief, some lasting mere years, others centuries. But the star won't reach these phases for a very long time. Right now, it's still in the calm before the storm of future burning. As the core contracts further, the outer layers will likely swell more. Betelgeuse may grow larger still, making its already enormous radius expand into an even more diffuse envelope. This will increase the star's mass loss, thickening the dusty cocoon around it. Observatories in the far infrared may one day see entirely new arcs forming, fresh layers of ejecta, marking new convective outbursts. You imagine these future arcs drifting silently away, forming faint halos that overlap with the ones Herschel already revealed. A star's autobiography preserved not in words, but in shells of gas and dust expanding across centuries. A surprising aspect of Betelgeuse's future is that the star may become more asymmetric than it is now. As the core heats, convection may grow more chaotic, plumes may become larger, surface temperatures may vary more dramatically. These changes would make Betelgeuse appear even more misshapen in interferometric images. Future astronomers may see patches so large and cool that the star seems half-shadowed. Spectroscopy may reveal stronger velocity fields. Light curves may grow more uneven. Pulsations may lengthen slightly or become multimodal in new ways. Betelgeuse won't become calmer. It will become more complex as it approaches new burning stages. You lying in your room, imagining this distant star changing across centuries, may find yourself feeling the immensity of time. Betelgeuse's future exists on a timeline so long that human lifetimes seem like quick breaths, and yet you're here, listening to its story unfold across hundreds of light years. One day, carbon ignition will trigger new instabilities. Deep within the star, fusion layers will shift rapidly. Shock waves will propagate outward. The star's outer layers may swell, then contract, then swell again. But from Earth, most of these changes will appear subtle, soft fluctuations in brightness and color. Some astronomers predict Betelgeuse may brighten slightly in the centuries before collapse. Others believe it may dim as dust production increases. The star's behavior is too complex for a simple prediction, but its ultimate direction is certain: inward, toward a hotter core, toward a future collapse. When silicon burning finally begins, millennia from now it will last only days. After that, iron piles up in the core. Iron cannot produce energy through fusion. Gravity wins. The collapse begins in less than a second. Neutrinos burst outward. A shock wave forms. The outer layers explode. A supernova blossoms. But none of that belongs to the Betelgeuse we see tonight. The light reaching you is from the late 1400s. The star you're learning about is thousands of years from its dramatic end. What you're drifting through now is a star in long, slow transition, not a star on the brink. This long timescale strangely softens the story. Betelgeuse is not a symbol of imminent catastrophe. It's a symbol of slow change, of ancient processes unfolding beyond human urgency. It reminds you that some transformations happen quietly, stretched across centuries. And yet, knowing what lies ahead someday gives everything you've explored a quiet tension. The star is not near the end, but it is moving, shifting, preparing. The future is woven into every pulse. And as its core tightens slowly in silence, you feel a different kind of silence forming around you too, one that leads gently toward a more reflective place, where the journey you've taken through this giant's life begins to circle back toward your own. As you settle again into the quiet of your room, the journey you've taken through Betelgeuse begins to gather itself into a single, gentle shape. You've drifted through the trembling surface of a star, through its convection cells, its drifting dust, its bow shock, and the tightening rhythms of a core preparing for futures far beyond your lifetime. The glow from that distant giant feels softer now, almost familiar, as though you've walked its long hallways and memorized the way its light moves. You lying there might still picture the huge convection plumes rising and falling beneath Betelgeuse's surface, slow giants of gas swimming upward in bright waves. Or maybe you're thinking about the dusty arcs curving around the star, like rings of memory suspended in space. All of it, every flicker, every pulse, belonged to a story unfolding long before humans existed, and continuing long after we're gone. Yet somehow tonight, it felt close enough to touch. You might remember the star's uneven heartbeat, the way it swells and contracts like something breathing through centuries, or the faint turbulence in the envelope, where molecules drift in cold silence, or the inner furnace shrinking, heating, tightening, moving toward futures too slow for human eyes. These images aren't just scientific explanations, they're impressions that linger in the mind, like echoes of a place you briefly visited. As you breathe now, you might feel a strange comfort in knowing that Betelgeuse isn't rushing. Nothing in its life happens quickly. Stars this massive unfold across millions of years, and even in their final chapters, they pace themselves with patience beyond imagining. The universe doesn't hurry, and you don't have to right now either. Your own worries live on a much smaller scale, and even those eventually soften with time. And maybe it feels grounding to realize that you've looked not only at the star's brilliance, but at its flaws, its uneven winds, its collapsing clumps, its chaotic outbursts. A star doesn't hide its instability, it shines through it. All its imperfections drift through space, glowing softly. There's a kind of honesty in that, a reminder that things don't have to be steady to be remarkable. If this quiet journey felt comforting, or if these drifting images helped you unwind, I'm grateful you spent this time here. And if you've stayed awake until now, I'd truly appreciate it if you could leave a like and subscribe. Both help this little corner of science reach others who might need a peaceful night too. And before you drift off fully, tell me in the comments where you're listening from and what time it is there. It's strangely soothing to imagine people around the world connected by the same starlight at different hours. As your eyes grow heavier, imagine once more that faint reddish glow of Betelgeuse shining from the night sky. Its light left the star over 6 centuries ago, traveling across dust, magnetic fields, and drifting arcs until it reached you, lying here with your thoughts. That journey of light mirrors your own, long, winding, shaped by invisible forces, but still moving forward. You don't have to hold on to every detail. You don't have to remember every number or every layer of the star. What matters is the feeling, the sense of scale, the softness of cosmic time, the reassurance that the universe is vast and patient and endlessly unfolding. Betelgeuse will continue its slow transformation, and you can let your own transformations happen gently too, in your own time. As the last of the thoughts quiet down, imagine the star fading into a distant ember, leaving only the warmth of its story behind. Out there, Betelgeuse continues to shift, pulse, shed, tighten, and evolve. And here, you're resting under the same sky that carries its light. And as the night deepens around you, you might feel the faint impression of that distant giant settling softly in your mind. Quiet, warm, ancient, like a small ember glowing in the dark, reminding you that even the brightest things in the universe move slowly and that you are allowed to rest.